Hey guys, this is Mr. Galoya. We're back again on this constant velocity note package. This will be the third video, and we're looking today at pages 5 and 6. And so here's kind of your note packet. You've got part of it filled out already. We've got the first 4 pages filled out. We've been talking about objects that move at one speed. We have a position time graph, and we get this nice little direct relationship, a slope, and that can tell us then how fast. We've come up with the equation that governs these objects. The displacement of the object is equal to the velocity times time. We get this equation from y equals mx plus b. We've talked about, more than one object on the same graph and making some comparisons. And we've talked about then more complicated position time graphs. If we have a negative slope, that means an object's going back towards the reference point. We have a negative velocity. We can have an object that has a horizontal position time graph. That means the object's at rest. We can talk about an object moving away and then stopping and then coming back towards the reference point. We've talked about distance versus displacement. Distance is the path length, or how far an object moves. Displacement is where did the object end relative to where it started. That'd be xf minus xi. Let's take a look maybe at page 5, and I want to show you another technique to get the motion of objects, or to discuss the motion of objects. Let me get a pen here to write with. If we could take a snapshot of something moving, a series of snapshots, we could come up with kind of a number line, and that's kind of what we'd like to do today, is show motion kind of on a number line here. And so we have this example from page 1. We had this car moving at 50 miles per hour, constant velocity. So there's our position time graph. The slope, we said, again, was the velocity of the objects, 50 miles per hour. So what we can do is take these points here really and create then this number line. This number line is given a special name. It's called a motion map. And it's just kind of a number line that shows kind of the motion of the object. And so at the very beginning, that's my reference point. We draw a point there, and then 1 hour, 2 hours, 3 hours, 4 hours, 5 hours. So these really represent timing dots. So this would be time equals 0 hours, time equals 1, etc., up to time equals 5. And what we can do is we could connect these dots kind of with arrows, and that shows the direction of motion. We're moving away from the reference point. Now, we can do a more complicated case, and we could maybe show several different objects moving on the same motion map or the same number line. So maybe we have runner A and we have runner B. Now, can you tell me kind of what's happening here? What's runner A doing? Well, runner A is starting at the reference point and is moving away from the reference point. Runner A then has a velocity that's equal to that slope, and we have points 5, 5 and 0, 0. So the slope of A is 1. So every second, runner A is moving 1 meter away from the reference point. So we can put those dots on. So this would be runner A. Again, these are the timing dots. Time equals 0, time equals 5. Now, runner B, though, is at 5 meters and has a negative slope. That means runner B is traveling back towards the reference point. Now, we'll have to then kind of maybe do this one above it, and we can do that. That's fine. So this would be the 0 timing dot for runner B. And again, we can put these dots in here, and this would be time equals 5. And runner B is going the other way. So that represents the motion map for these two runners. Now notice, this gives us information that we kind of lose here. You know, we said that this intersection point's kind of an important point. What did we say that meant? Well, again, the intersection means that's the point along the race that the objects are at the same location. So at 2.5 seconds, both objects are 2.5 meters away from the reference point. Well, let's maybe go to page 6 here, and let me have you maybe make some motion maps. And let me change my color here. Can you kind of make a motion map of this top one? So again, what we need to do is come up kind of with the slope, the equation. So in this case, we have an object that's starting at 5 meters. So this would be my time equals 0 dot, and the object then ends up at a position or at the origin at 4 seconds. All right, so we could draw a timing dot there. That would be t equals 4 seconds. Now we need to get the dots kind of inside here, don't we? Now, to kind of help us with that, we would find it helpful to maybe have the equation. Well, so we're saying then, you know, xf equals vt plus x sub I. Well, we know what the initial xi is. That's 5, right? So that'll be 5. That'll get popped in here, 5 meters. The velocity then represents the slope. So we have 4, 0, and we have 0, 5. So the slope would be 5 minus 0 over 0 minus 4. So that slope is negative 5 over 4. You know, if you put that in your calculator, 5 over 4, we get a slope of 1.25, but it's negative. So that represents your equation. Remember, we leave t as a variable, and we leave x sub f as a variable because we can put in different times. So at 1 second, it looks like we're between 3 and 4, pretty close to 4, but it's not equal exactly. So we can put 1 second in here, and we would then have x sub f equals negative 1.25 plus 5, and all this would be in meters. So that'd be 3.75, right? So at 3.75, that would be our first timing dot, or timing at 1 second. And at 2, we put the time in, so we end up then with 2.5. See, that's right in the middle there, 2.5. And then the third timing dot, we would have 5 minus 1.25 times 3. Okay, 3 times 1.25 is 3.75, so we're left at 1.25 here. Do you understand how to use your equation? And the object is going back towards the reference point, so we can put in these arrows. Okay? So what happens if an object has this sort of position time graph? Well, the object is moving away from the reference point. So we can have t equals 0. And at the second timing dot, we're now at 3. Okay, so what happens kind of in the middle here? Well, our slope is basically the object is moving 3 meters in 2 seconds, so our slope is 1.5, right? So at 1 second, we're 1.5. Okay, do you get that there? Now, at 2 seconds, the object rests. So we can't really put the dot right on top there, so we can put it kind of above there. So at 3 seconds, t equals 4 seconds, and t equals 5 seconds. See, the object is at the same position, 3 meters. The object rests there. So we can draw a couple of arrows. Then we don't need any more arrows because the object's not moving. Okay? Does that make sense? I hope you're kind of getting this. We can do the same thing here. So at t equals 0, the object's at 0. At 1 second, the object's at 3. Okay, so we can draw an arrow there. Well, between 1 and 2 seconds, the object rests. So I can draw that above. That would be t equals 2. And then the object then the object will go back to 4 meters. I'm sorry, the object will come back to the reference point at the 4th time interval. So the object comes back this way, so t equals 4. That'd be 4 seconds. And right in the middle there, we'd have t equals 3. So now we need to draw an arrow in the opposite direction on our motion map. So does that kind of make sense, how to draw a motion map? So again, let's have a recap. We've got these position time graphs. They're showing us positions in time. Well, that's great. That's helpful. You know, we can get slopes, we can get equations. However, we can also deal with these things called motion maps. And these motion maps are really just number lines. Now, I'm bringing this up because we have an instrument that can help us and can make motion maps of objects. It's called a ticker tape. And I'm going to show you how to use this over the course of this unit. And we can use it to help us get the speeds of objects. Hey, that ends notes for part 3. And we got just a couple more pages to do, and we'll do that in the next video. We'll talk to you later, kids. Bye.